Section 6.5, Average Value of a Function. The title of this section is essentially stating that if a function has varying outputs over an interval, what would be the average value? We could figure this out by adding a bunch of values in an interval and then divide by how many we added. Essentially just take a bunch of output values, add them up, and divide by how many we added. Same idea that you would find the average of any quantity. But we could make this better by dividing the interval into n subintervals. You're seeing a theme now over chapter 5 and 6. This theme actually continues into Calculus 2 as well, of just splitting things up to then see how we can use the fundamental theorem of calculus. So let's take the interval, divide it into n subintervals, taking each function value at each subinterval, adding them up, and then dividing by n. That's the number of things that we added up. But since we know that delta x is the same thing as b minus a divided by n, where a is the beginning of an interval and b is the end, and n is the number of subintervals, we could then rewrite n as b minus a divided by delta x. So we could add up all of the n function output values and then divide by this fraction for n. What that would look like using some of the notation we've seen is f of x sub 1 star plus f of x sub 2 star plus all the way up to f of x sub n star. There's your n function values. Divide that by n. Dividing by n is the same thing as multiplying by the reciprocal of b minus a divided by delta x. The reciprocal of that would have b minus a in the denominator, which means you could write 1 over b minus a times the numerator from the previous fraction, which is the sum of all the function output values, and then delta x would also be in the numerator, and there it is at the end. We can then factor out the 1 over b minus a and use sigma notation for the sum of all of those function values. So really this average just looks like 1 over b minus a times sigma, where we're adding from I equal 1 to n of the f of x sub I star values, and then delta x. If we take the limit of this expression as n goes to infinity, then we get the definition. The average value of a function f on the interval ab is simply denoted f with a subscript ave for average, and that is just 1 over b minus a times the integral from a to b of f of x dx. So you're essentially just taking the area under f of x over an interval and then multiplying by 1 over the distance between the two interval points, a and b. So let's see how that works with this first example. Find the average value of the function f of x equal to 1 plus x squared on the interval negative 1 to 2. So here f sub ave would be 1 over b minus a would be 2 minus negative 1, and then times the integral from negative 1 to 2 of the integrand 1 plus x squared dx. The fraction out front becomes 1/3. I can use my antiderivatives. Antiderivative of 1 is x. Antiderivative of x squared is x cubed over 3. And then I'm evaluating at 2 first and then negative 1. So this gives me 1/3 times, first plugging in 2 plus 2 cubed, which is 8/3, minus, and then I would have negative 1, and then negative 1 cubed is negative 1, so minus 1/3. And so I'm just going to be subtracting negatives, which turns into addition. So then I have 1/3 times 2 plus 1 is 3. 8/3 plus 1/3 is 9/3, which is also 3. So I'll have 1/3 times 6, which is 2. All right, very simple formula. Let's see how that applies to a theorem. Here we have the mean value theorem for integrals. We've had the mean value theorem before earlier in this class. Now we get a similar sort of relationship that's relating to integrals. If f is a continuous function on the interval ab, then there exists a number c in the interval ab such that f of c is equal to the average value of the function, which means f of c is equal to 1 over b minus a times the integral from a to b of f of x dx. Or you could quite simply write this as the integral from a to b of f of x dx is equal to f of c, the average value, times b minus a. What this essentially says is for a continuous function, there is a value c such that f of c is equal to the average value of the function. As a specific contextual example, you could say that there is a time in the day when the temperature outside is equal to the average temperature for that day. Let's look at another example that I took from the homework that relates to this theorem. Use the mean value theorem for integrals to find the point on the curve which takes on the average value of the function. So find c such that f of c equals the average value of f of x, which is equal to 4x plus 4 over the interval from -6 to -2. So first, let's find the average value. So f sub ave, as we saw in the previous example, 1 over b minus a, that would be -2 minus -6, times the integral from -6 to -2. And our integrand is 4x plus 4, and we're integrating with respect to x. So then the fraction out front becomes 1 over -2 plus 6, so 1/4. My antiderivative of my integrand, antiderivative of 4x is 2x squared. Antiderivative of 4 is 4x. And then we're going to plug in -2 first and -6 second. So 1/4. Plugging in -2 first, I would have 2 times -2 squared, so that's 8. Plus 4 times -2, which is subtracting 8. And then I'll subtract, now plugging in -6. 2 times 36 is 72. And then plus 4 times -6, so that turns into minus 24. So then I have 1/4 times 0 minus, and that'll be 48. So 1/4 times -48, which is -12. Okay, so I found the average value. Now find a value c such that f of c equals the average value. So first of all, if f of x is equal to 4x plus 4, then f of c is just quite simply plugging in c for x. And we want to solve f of c being equal to the average value of the function. We found the average value of the function was -12. So then f of c is 4c plus 4. The average value was -12. And then the value of c, subtract the 4 first, then divide by 4, and we get -4. So that answers the question. And what this means is that we've got our interval from -6 to -2. When essentially x is equal to -4, somewhere in that interval, the function is equal to its average value. F of x is equal to its average.